Okay, chapter 7. It's methods in differential equations. So we're going to look at how to solve differential equations. So a quick recap, first of all, of the method of that you should be familiar with from the year 2 pure maths course. So the first of all, actually, this is from year 1. You should be able to solve anything like this. So to solve a differential equation, by the way, differential equation will contain the derivative dy dx, and the second order differential equation will contain the second derivative also, so d to y dx squared. So this one actually is a basic differential equation. So you are trying to find what function differentiated gives you f of x. So you are undoing differentiation. So you are going to integrate it. So when you integrate dy dx, you are going to obtain y, and then it will be equal to the integral of f of x. So this is the basic differential equation, standard question from year 1. We have to find the function. Now, this method here is when you have two functions. Let's actually say this one. So it's different. So you've got dy dx, so it's the first order differential equation, and you've got a product of a function of x, let's say f of x, and a function of y, let's say g of y. Now it could be a product or a quotient. Okay, so you could have f of x divided by g of y. So you are going to rearrange this using the separating variables method. So we are going to separate that's the method's name. So to separate the variable means move rearranged in such a way that you will have all y's on the left hand side and all x's on the right hand side. So y's go on this side and x's go onto this side. You can only rearrange only by multiplying or dividing, so never by adding or taking away or square rooting, anything like that. So these are the only two operations you're allowed to carry out. So first of all, dy dx needs to be separated. So dx is on the bottom here. It needs to be treated like a fraction, so as if you multiply this dx onto the right hand side. Okay, now here you've got f of x multiplied by g of y. You only want to have x's on the right hand side, so you want to have x's wherever the dx will go. So you will have these elements onto that side because dx will multiply onto the right hand side. Now g of y, to get rid of that, we're going to divide by g of y. So we'll have 1 over g of y dy dx. Dy, because dx has gone. Now to make it legal, we are going to integrate. Okay, so we separate the variables and then we put the integral symbol, and then you have to integrate with respect to y on one side, integrate with respect to x on the other side. You're going to put plus c on one side only, and normally it will be on the side that x's are. The side with x's. Okay, so let's have a look at some questions, examples from beginning of the chapter 7. So the first example deals with dy dx equals minus y over x. We are going to find the general solution to that equation, and then we're going to sketch a member of the family of solution curves represented by the general solution. So the first thing we're going to do, we can split the x's onto the right hand side and the y's onto the left hand side. So we're going to multiply dx onto the right hand side, and we are going to have dy's on with y's on the left hand side. So y is going to be moved onto that side into the denominator, so you divide by y, and you obviously will be left with minus 1 over x. To make it legal, we are going to put the integral symbol in front of this those terms, both sides. Okay, so now all we need to do is integrate 1 over y, so that goes to ln of modulus of y, and this is minus ln modulus of x. Obviously we need to put plus c. So we'll put all the ln's together, so ln y plus ln x on the left hand side and c on the right hand side. We can, adding the logs means you can write it as a single log of the product, and then we can rearrange it. Now you have an option of replacing c with ln a, or you could just rewrite it modulus of y times x is equal to e to the power of c. That can be replaced with a constant a, so that's clearly always greater than 0. So over here, the meaning of the modulus, it can be equal to a or minus a, since it's positive. So you will have y altogether is equal to plus or minus a over x. That will allow us to draw the curves. So imagine a being equal to 1, then we need to draw 1 over x as one of our possible solutions. If it's equal to 1, you can also have the minus 1 over x. Now if a is equal to 2, it will be 2 over x, so it's slightly steeper, which means it's further away from the origin. Now if a is equal to a half, it will be closer to the origin. So I've drawn these graphs, that will do. There's infinite number of these. This is the family of curves. So obviously, depending what a is, this will give you one particular solution. So if a was 1, we would be drawing the first graphs. Okay, so let's have a look at example 2 from this chapter. So in this example, we've got to find the general solution to the following differential equation. So x cubed dy dx plus 3x squared y is equal to sine x. And clearly we cannot here separate the variables, because there's no way we could split dy dx and be left with all the x's on one side and y's on the other side. It's just not possible. So then the second thing we could check is whether over here the left hand side is a result of a product being differentiated. And what you are going to look for is, first of all, focus on dy dx. That's part of the first term, and then you're looking for that the integral of that, so y onto the other side. Have you got it? Yes, you have. So imagine in our uv differentiation, so the product rule would be vu dash plus uv dash. So you're looking for a function that was differentiated. So if that was u and that was u dash, that could be the first step. So that means the other way around must be also true. So this one must be v dash, and therefore v must be this one. And is that the case? Yes, it is. It's definitely this is the differentiated x cubed. So that means that the function that was differentiated with respect to x was the product of x cubed, so these two together, multiplied by y. So now we are going to undo it. We are going to integrate it. So means undoing differentiation. So you're left with x cubed y and that's equal to the integral of sine x dx. So we've got to now integrate sine x, which goes to minus cos x. Obviously we'll put plus c. Now carefully now we'll make y the subject, so we are going to either multiply it by x to the power of minus 3 or divide it by x cubed. So you could write it as x to the power of minus 3 multiplied by minus cos x plus c, or you could say y is equal to minus cos x plus c over x cubed, anything like that. And make sure that you protect this with brackets if you choose the first option. So this is a general solution, general because it has c there. Okay, so for the next section we are going to look at a new method. It's called the integrating factor. So I'm going to go through the method first, and then I'm going to explain why it works. So if you have a differential equation of order 1 and it's after rearranging, or maybe it's already given, can look like this. So you can see you've got y and then dy dx on its own, and you've got some function of x, and then here we've got 1 in front of this, and you've got a function of x on the right hand side. Then we're going to use the method of integrating factor. So first of all, how does it work? The first step is to rearrange into the required form. What does it mean? So rearrange it into this form. Okay. Second, you're going to find the integrating factor. So the integrating factor is found by taking e to the power of the integral of the function that y is multiplied by, so px. Just make a note, do not, once you've integrated that power, do not put plus c here, no need. Okay, third, you can straight away go and use the following result. You've got to write y times the integrating factor is equal to the integral of q of x multiplied by integrating factor dx. So that is your key result. And then you integrate the right hand side, and then you put, obviously we put plus c, and you rearrange to make y the subject if that's what you've been asked to do. Okay, so we'll do the first example and then explain why this works. Okay, so in the first example, we've got a function dy dx, and then you've got minus 4 times y is equal to e to the power of x. So it's clearly that form. Your p of x over here is equal to minus 4, q of x is equal to e to the power of x. So the first step is done, it's rearranged already in the correct form. The second step is to identify the integrating factor. So it's e to the power of the integral of p of x, so minus 4 dx. Now the integral of minus 4 is simply minus 4x, so it's e to the power of minus 4x. Then all you need to do is step straight away to the following result. So the y times the integrating factor is equal to the integral of q of x times the integrating factor. So y times e to the power of minus 4x is equal to the integral of e to the power of x times e to the power of minus 4x dx. So it's y e to the power of minus 4x is equal, this is going to be the integral of e to the power of minus 3x, which is minus a third e to the power of minus 3x plus c. All we need to do now is get rid of that e to the power minus 4x, so multiply everything by e to the power 4x. So you'll have y is equal to minus a third e to the power minus 3x times e to the power 4x plus c times e to the power 4x. So just tidy it up a little bit better. That's the general solution to this equation. Okay, so the next example, we'll do those two examples first, and then I will explain how why that works. So the general solution to this particular differential equation, first over the differential equation. So I'm going to think, can I use integrating factor? So I'm going to attempt to rearrange it into the form, so dy dx is by itself, so I'm going to divide everything by cos x. So I'll get dy dx plus 2y sine x over cos x, and then you've got cos to the power 4x divided by cos x. So this here is equal to tan x, so you've got dy dx plus p of x is going to be 2 tan x times y, and over here one of the cos's will cancel, so you've got cos cube x. So the integrating factor is e to the power of the integral of 2 tan x dx. Now tan x integrates, and that's from the formula booklet, to ln sec. So over here we will have e to the power of 2 ln sec so that's equal to e to the power of ln sec squared x, because the 2 becomes the power, so that's equal to sec squared x. So that's the integrating factor. So let's go for the final result, well, almost final result. So straight away, y times the integrating factor, so it's y times sec squared x is equal to the integral of whatever we've got on the right hand side, so cos cubed x multiplied by sec squared x. So sec squared x, remember, is cos, that's going to be cos cubed over cos squared, that cancels to cos x, so the integral of cos x, so it's y sec squared x is equal to positive sine x plus c. So you could multiply it by, divide by cos squared, or multiply it by cos, so multiply by sec squared or times by cos squared, whichever way you want to write it down. So that's the general solution. For part B, let me just grab another piece of paper. We're going to find a particular solution to this equation, given that y is equal to 2 and x is equal to 0. So the solution of that we had was y equals, that was the general solution. So to find the particular solution, we are going to substitute x and 0 and y as 2. So 2 is equal to cos 0 squared sine 0 plus c. Cos 0 squared is 1 squared, that's 0 plus c. So that gives us c is equal to 2. So particular solution there you go. So that is the solution to example 4. and therefore you'll be able to go to exercise 7a. Now let's just briefly, before you do that, go through the reasoning why the integrating factor works. So there's the rearranged form, and very often students ask me, why is it that we have to find the particular integrating factor of that form? Okay, so what I'm going to do is show you what happens there. The idea is that you multiply everything once you find that integrating factor by the integrating factor. So you will have dy dx multiplied by integrating factor plus px multiplied by integrating factor y. I've just squeezed it inside there, and then q of x multiplied by integrating factor. And then you are going to imagine this, what you are creating this as the product rule that was differentiated. So what would that product be? What was the product that was differentiated? Because we are going to be undoing it. Okay, so what we are going to do is think about those functions. So you've got dy dx, and then you've got y. They go together, so they could be your u's. So u could be y, and u dash is dy dx. Therefore, this must be equal to v, the integrating factor, and v dash must be the integrating factor times p of x, or p of x times the integrating factor. So is that the case? What have we got as the integrating factor? So our integrating factor, which represents the function f, in our case is, we are asking you to find it to be the e to the power of the integral of p of x dx. Now let's actually try and differentiate it. To find v dash. So when you differentiate the function of e, it goes to itself. So that's our integrating factor. But then it's multiplied by that integrating factor differentiated. So by the power of the integrating factor differentiated. So we need to differentiate the power, so that's the inside function. And that's what happens when you differentiate e to the power of f of x. It goes to f dash of x, if that's your power, times e to the power of f of x. Okay, so but what have we got here? We are differentiating the integral. So these two undo each other. So you're left with p of x times e to the power of p of x dx. So we are actually left with p of x times the integrating factor, because that is the integrating factor. There you go. So that proves that this method creates the differential of a product of the function u, which is y, and the integrating factor. So somebody must have differentiated this. So we are going to think of that as that was differentiated. There you go. And now we need to integrate. So when you integrate it, you're left with y times the integrating factor, and then you just do the integral of q of x times the integrating factor. So that shows you how this method works. Okay, so off you go, do all the questions in exercise 7a.